Let's continue with studying solutions to the Einstein equations. In order to explore the richness of the solutions of the Einstein equations, it's not sufficient to just speculate. The best guidance is to have some exact solutions, even if they are solutions with very high symmetry. So overall, the task is to solve the equations of motion of matter along with the Einstein equations. And in practice, this problem is way too hard. And so we need to reduce the number of degrees of freedom that are in the problem. And that is done by imposing symmetry assumptions. The big question is, how much can we weaken the symmetry assumptions of Friedmann-Lemaitre spacetimes and still get exact solutions? So we're back to cosmology now from black holes. The strategy will be this. We will classify cosmological models given by a Lorentzian manifold along with an energy momentum tensor. We will classify those models by the amount and by the type of symmetry that they have. It turns out that a lot of exact solutions are known, and some of them have some really weird behavior. For example, it turns out that among the high symmetry models, some are very different from FRW spacetimes, but during some periods of time come arbitrarily close to FRW spacetimes. That's a little worrying, because it means that FRW spacetimes are not really stable. There are solutions in their neighborhood which have weird behavior towards the future or towards the past. There is a text on these considerations which was written by John Wainwright and George Ellis. That's the same Ellis as the one who wrote with Hawking a book on GR. Wainwright was, by the way, the chair of department here in Applied Math who hired me, but not for cosmology. He's retired now. Okay, so we're going to look at the solutions to the Einstein equations with symmetries. And symmetries are intimately related to Killing vector fields. Let us study Killing vector fields a little more deeply then. Two spacetimes, mg and m tilde g tilde, are isometric and therefore describe the exact same spacetime or the same pseudo-Riemannian structure if there is a diffeomorphism that maps also the metric into the metric. And we say that spacetime has a symmetry if we find such a diffeomorphism for the manifold that maps the manifold into itself and maps the metric into itself. So for example, consider a manifold in the shape of a can. And here's a point on that can. So it could be just like a pop can. So it has a rotational symmetry. And consider a point on that can. Now we define a diffeomorphism that maps points of the can into points of the can in such a way that you just go around a little bit in an angular fashion. So for example, this point is mapped into that point that you obtained by just rotating the can a little bit. And so every point is mapped into an image point that's obtained by just rotating the can by a certain angle. Our diffeomorphism then performs a rotation of the manifold about some symmetry axis, and the manifold is mapped into the manifold, and the metric also doesn't change. Mathematically, the set of all symmetries of a manifold forms a group. And just to remind you of the structure, a group is a set with an operation that... I'm putting those details here just to make sure everybody knows about these things, because we are talking about groups, Lie groups, and Lie algebras now. So a group is a set which has an operation, let's call it little circle, and the operation takes two elements of the group into the group. A group must be a set which also has a neutral element, let's call it E, that obeys the condition that it's a right neutral element and a left neutral element. The group's multiplication has to be associative, and there has got to be an inverse. Any set that obeys those axioms is called a group. Now, a group is called a Lie group if on top of fulfilling these axioms, the set also fulfills the axioms of a finite dimensional smooth manifold. So if the elements of the group obey these axioms and on top of that form also a smooth manifold, then this is a Lie group. For example, consider the set of rotations in R3. The set of rotations in R3 forms a three-dimensional Lie group called SO3. And why is it three-dimensional? Well, there are three parameters needed to specify a rotation in R3. You need a polar angle, you need an equatorial angle to specify the axis of rotation, right? So you say it's this much down from the North Pole, this much angle in the equatorial plane, and then the third number is how much you actually rotate about that rotation axis. So you have three angles that describe a rotation in R3. And there's of course a continuum of these rotations, and that makes the set of rotations not just a group, but also a manifold. The symmetries of a manifold can also be discrete, for example, reflections. A manifold may have some sort of reflection symmetry that would be discrete, but very often, and that's our main interest here, the symmetry group of a manifold is actually a Lie group. And what we will now explore is how that has to do with Killing vector fields. So remember that by assumption, the group of symmetries or isometries of a manifold consists of elements H, each of which is an isometric diffeomorphism. So each group element of the symmetry group maps the manifold into itself. It maps points of the manifold into points of the manifold in such a way that the metric is mapped into itself. Now, let's consider the set OP, which is a subset of the manifold, which is defined to be the set of all points that you can get to in the manifold from a starting point P by applying all elements of the symmetry group. OP will be called the orbit of P under the action of the symmetry group. So for example, if we go back to this case here, we have the symmetry group of the rotations of the can along the vertical axis. And so no matter by what angle we rotate the can, we get an isometry. If we take this point here and we apply an arbitrary symmetry transformation, so an arbitrary rotation, then we map it onto points all around the can here. So the orbit of that point is literally, some sort of equatorial line. But more generally, if you start with a point P, then the set of points Q of the manifold, which are such that there exists a group element, so that the group element maps P into Q, that set of points of the manifold is called the orbit of P. It's all those points that P gets mapped to by group operations, by symmetry group operations. Okay, so O of P is the orbit of P under the symmetry group. Now if G is a Lie group, so it's a smooth manifold, then each orbit of a point P, or each orbit of all of the points P, is a submanifold of the manifold, or maybe the orbit is just a point. It could be that the symmetry group is not mapping the point into another point, but just into itself. Consider the can again. If you take the point which is just on top in the middle, under rotations, it goes into itself. So its orbit is just itself again. That can also happen. So for symmetries that are Lie groups, we have that the orbit is either a submanifold or it's just a point. So we looked at the isometric diffeomorphisms. What are the infinitesimal isometric diffeomorphisms? And if the finite isometric diffeomorphisms form a group, what kind of structure do the infinitesimal ones form? Mathematically, what are they? Turns out they are a Lie algebra. Remember the Lie derivative. The Lie derivative in a direction of a tangent vector field psi of some tensor is given by this expression, where you can either use the covariant derivatives or you can use the ordinary derivatives. Both equations hold true. The Lie derivative of a tensor gives us the rate of change of that tensor's coordinates along the flow generated by along the flow of diffeomorphisms phi, which are generated by the vector field psi. So this is the change of Q under diffeomorphisms generated by psi. Let us use the Lie derivative to calculate the change of tensors under the diffeomorphisms generated along symmetry group orbits. So if psi is along a symmetry group orbit, then the Lie derivative of the metric will vanish. If psi generates an infinitesimal, if psi generates an isometric diffeomorphism, then the isometric part of that is to say that the Lie derivative of the metric doesn't it vanishes. And if we spell out what that is, we obtain that the Lie derivative of the metric being equal to 0 means that, well, this is the Lie derivative of the metric by the formula that we had just above. Now, the first term here has the covariant derivative of the metric, and that is vanishing. Remember, that was the consistency condition between the affine connection and the metric. So that first term is vanishing. Therefore, to require that the Lie derivative of the metric is 0 is to require that the sum of these two terms is vanishing. And I hope you remember that this is also how we derived earlier on what Killing vector fields are. So a vector field psi generates a symmetry or an isometry of space-time if it is a Killing vector field, namely if the sum of these two terms is vanishing. If we pull down that index, then the metric tensor drops out of this expression and we just have this. So this is the differential equation for killing vector fields. Now, what is the maximum number, d, of killing vector fields in an n-dimensional manifold? Previously in this course, I just mentioned the number. Now let's derive how that comes about. The number is n times n plus 1/2. This is how many killing vector fields an n-dimensional spacetime can maximally possess. And to count that, to prove that this is so, let's consider that there are two ways in which the killing vector equation can be fulfilled. One way to fulfill it is to have that these covariant derivatives vanish individually. So if we have that psi mu semicolon nu is equal to 0 for all nu, so if the absolute covariant derivative of psi is equal to 0, well then clearly if this alone is vanishing and that alone is vanishing, then that makes it a killing vector field. Now we can have maximally n such independent vectors. We can have maximally n vectors that are independent. And I mean, just generally, we can only have n. And in addition, we want them to fulfill that condition. On the other hand, these covariant derivatives may not be vanishing, and the left-hand side then has to be 0 by virtue of this being antisymmetric. So if the absolute covariant derivative of psi is not vanishing, but if k mu nu, being that twofold covariant tensor, is antisymmetric, holds, then we also have a killing vector field. How often can that happen? Well, that matrix is antisymmetric. It's an n by n antisymmetric matrix, and therefore it has n times n minus 1/2 independent degrees of freedom. So if we tally this up, we obtain n ways of getting killing vectors from the first possibility, and maximally n times n minus 1/2 from the second possibility. That gives us a total of n plus n times n minus 1/2, which is n times n plus 1/2, as the maximum number of killing vector fields. Yep?
I think there's also another way of seeing this. You always have like n translation symmetries, and then you have n choose 2 rotations, including all.
We will get to that.
Okay.
Exactly. This has to do with translations versus rotations, exactly.
Yeah.
And so,
That's interesting.
yeah, and we will get to that now. Okay. Now, what's the relationship between the symmetry Lie group and the symmetry Lie algebra? I have to define what I mean by Lie algebra. I mean, many of you may know, but I just want to make sure that we're all on the same page. Here's the general idea. A Lie group is a smooth manifold which has an extra structure. It also has multiplication. I mean, previously, 2 slides ago, I put it the opposite. I said it's a group which also has an additional structure, which is that it's a manifold. But you can also view it as a Lie group is a manifold which also has an additional structure, which is a group multiplication. Now, the product of group elements gives you another group element. If you take the product of group elements which are close to the identity, then that gives you group elements close to the identity.
So why is multiplying by 1 give you something near 1?
If both of them are close to the identity.
Close to 1. Okay.
Yeah. No, otherwise not, yeah. Yes. Now, let us consider the tangent space to the point of the manifold, which is the identity element of the group.
What do you mean by close to here?
Infinitesimal distance. In practice, I mean this. So we're looking at the tangent space. So we're looking at the tangent space to the identity element of the group. This is a vector space. And this vector space is ordinarily, for a differentiable manifold, it's just a vector space, just a tangent space. But because the differentiable manifold here is not just a differentiable manifold, it also has a product structure on it, because it has the group structure on it. It turns out that the tangent space is inheriting some of that structure. Because you can multiply group elements, and therefore multiply points on the manifold, there's also multiplication in the tangent space that you can think of as arising from the exponential map. Now, we then define the Lie algebra of a Lie group G to be, as a vector space, the tangent space at the identity element, and on top of that, it's not just the tangent space, it also is equipped with an inherited multiplication. A multiplication that traces back to the multiplication in the group. And it turns out that from the knowledge of only the Lie algebra, only this tangent space, vector space structure, plus that inherited multiplication, the group can then be reconstructed from that. Again, think about it, it's like basically the exponential map. Although it may not be always unique, the way you get from the Lie algebra to the Lie group. So in the following, see, this is just a quick overview. Can't go into all of the details. Let us now collect the properties of that inherited multiplication. What is that multiplication that the tangent space inherits from the entire group manifold? And these properties of that multiplication can then be viewed as the defining properties of a Lie algebra. And you can start with a Lie algebra and then define from it what the Lie group is, or you can start with the Lie group and, as we did it just now, then reduce that to a Lie algebra. You can go both ways. So a Lie algebra is, by definition, any set which obeys the following axioms. A Lie algebra is a vector space, let's call it A, which has a multiplication on it. This will be the inherited multiplication from the Lie group. But that multiplication is denoted by curly brackets. This multiplication takes two elements of the Lie algebra, therefore two elements of the tangent space, and maps them into an element of the Lie algebra, but in a quite non-trivial way. It has to be anti-commutative or anti-symmetric. You see, we don't have a multiplication other than this one, so I shouldn't say anti-commutative. This is an anti-symmetric multiplication for all elements of the Lie algebra. And also, this multiplication has to obey the Jacobi identity here. Remember that all linear transformations, all linear maps, all matrices, all operators, all linear operators obey the Jacobi identity. And eventually, the elements of the Lie algebra, we want to be able to represent them as generators of translations, generalized translations and rotations, generators of the group action, and therefore they need to obey the Jacobi identity, which ensures that they can be represented in this way. Every vector space A with a multiplication that obeys those axioms is isomorphic to the tangent space at the identity of a suitable Lie group. Now, the set of Killing vector fields of a space-time forms a Lie algebra. The set of Killing vector fields obeys all of those axioms. I leave it to you to prove that this is so. So what you have to prove is that these axioms hold. So we must have that if you take a Killing vector field, multiply it with a number, it's still a Killing vector field. If you add two Killing vector fields, it's still a Killing vector field. This is the axioms of a vector space. But then you also must have this anti-symmetry here, and you must have the Jacobi identity. So assume, for example, that Xi1 and Xi2 are two Killing vector fields of a manifold. So let's assume that a manifold has two Killing vector fields. Then let's consider an arbitrary linear combination of them. So we want that is a that this is a Killing vector field again. It's a little work to check that. And then when you take the Lie bracket of them, so when you multiply them with a Lie multiplication, then I mean, how do you define the Lie bracket of Killing vector fields? Well, by definition, we write the Lie bracket in this way as the execution of Xi2 and then Xi1 afterwards minus the other way around. Remember about 10 or so lectures back, we proved that this combination, the anti-commutator of vector fields, is a vector field again. That's quite non-trivial because each one of these guys involves a first derivative. But we apply them twice, so we get second derivatives involved. But because it was anti-symmetric and the x and the y derivatives commute with each other, the second derivatives actually dropped out. So this is actually, by a thing that we proved, by a little theorem that we proved much earlier, it's guaranteed to be a vector field, but is it a Killing vector field? I have to prove that. And also you need to prove that the Xi obey the Jacobi identity. All those things can be shown, and so we have that the Killing vector fields really form a Lie algebra. And it's the Lie algebra of the Lie symmetry group. So it's basically the tangent space to the symmetry group at the identity with the inherited multiplication. So the big picture is that the symmetries of any Riemannian or Lorentzian manifold form a group. They can be concatenated associatively, it's an associative multiplication, and they possess an inverse, so that makes them a group. These symmetries, some of those symmetries are differentiably parametrized by a flow, and so we get a Lie group, and each Killing vector field is the infinitesimal generator of such a Lie group symmetry. Okay, so every Lie algebra generates a Lie group. Now we get to what Guillaume was anticipating. We can think of those symmetries of a space-time as, roughly speaking, of two kinds. There are translations and there are rotations. But of course, translations and rotations in a generalized sense. For example, rotations could also be Lorentz transformations. And it could be much more complicated than that too, depending on what the space-time symmetry structure is. So let R be the dimension of the Lie algebra. And therefore also the dimension of the Lie group. The dimension of the tangent space is the dimension of the manifold. So the dimension of the Lie algebra is also the dimension of the symmetry group. Now, remember this definition. we said that the set of points that a point P can flow to under the symmetry transformations is the orbit of that point. So the orbit of a point is the set of points that P can flow to along the Killing vector fields. So O of P the orbit of the point P will have a certain dimension. Remember, some points may have an orbit which consists just of the point, in which case the orbit has dimension 0, it's just a point. But in general, a point will be mapped into some orbit which has some dimension, and that dimension can be at most as large as the dimension of the spacetime itself. Let's call that dimension S. So S is the dimension of the orbit of a point. The dimension of an orbit cannot be larger than the dimension of the symmetry group. So if R is the dimension of the symmetry group, then the dimension of the orbit can be at most as large as that, but it doesn't have to be as large as that. You could have, for example, an example of the can before. The symmetry group is just rotations about one axis. That's a symmetry group U1. And it's one-dimensional, but if you take a point in the middle of the can, its orbit is zero-dimensional. So you could have that the orbit has 0 dimension and the symmetry group has dimension 1. Here is the same thing written out a bit more mathematically. Consider, for example, the manifold as being R2. The point in question, whose orbit we're interested in, is just the origin. Then the maximum number of Killing vector fields that we can possibly have in a two-dimensional manifold is 3. Remember the general formula that we had before, n times n plus 1/2. So it's 2 times 3 over 2 is 3. It's the maximum number of Killing vector fields that we have here. So we have a 3-dimensional Lie algebra of Killing vector fields, because in fact we actually have 3 Killing vector fields in the case of R2, and the 3 Killing vector fields are given, for example, by these 3. So we have Killing vector field number 1, which is just the tangent vector in this direction, tangent vector in the y direction, and also this one. And what do they generate? What if we use the exponential map? What if we exponentiate them? Well, if we exponentiate this one, we get translations in the x direction, translations in the y directions, rotation about the origin. Okay, so we have these 3 Killing vector fields. And what is the orbit of the point which is sitting at the origin? Well, the orbit of the point at the origin is R2, because the generators d by dx and d by dy generate flows in the x and the y direction, arbitrary amounts. So the point P can be moved anywhere in R2. Yes?
So you have the example of the can with the rotation, and you have points that stay stable. Is it the case that there's always at least one point that equal dimension between the group and the orbit? Dimensionality of the group and the orbit?
I'm not sure I'm getting that.
So in the can, you still have, if you took not one of the points along the axis of rotation, you'll still get the one-dimensional thing.
Yes.
So can you have a symmetry group that every point has a smaller dimensional orbit than the dimension of the group?
I don't know that. Let me see. Yes. Yes. Right. Take for example rotations in R3 on the sphere. So you have the sphere, and it's two-dimensional. The rotation group is three-dimensional, and every point on the sphere has only a two-dimensional orbit, which is the size of the sphere. Right, but let's get back to the plane. We have three Killing vector fields, and we have that the orbit of a point, such as the point at the origin, is R2 because these generators give us diffeomorphisms which are translations in the x direction, translations in the y direction, any combination of them, and so we can get our point P anywhere. So the surface of homogeneity, the so-called surface of homogeneity, has therefore dimension 2. So P gets mapped into a surface of homogeneity which has dimension 2. It's the space of the set of points where you can get by translations. So the surface of homogeneity technically is generated by those Killing vectors, in this case K1 and K2, which do not have trivial orbits. Okay, so this Killing vector doesn't have a trivial orbit. It maps every point into another point. This Killing vector maps every point into another point. This Killing vector doesn't. It has a point that it maps into itself, which is the origin. The surface of homogeneity is generated by those guys that do not have trivial orbits. And the space that is generated by those two guys is two-dimensional. So this dimension of the space of homogeneity is 2. By the way, notice just a technical thing that you may want to be aware of. Our space is two-dimensional. At every point, therefore, the tangent space is two-dimensional. Therefore, there can only ever be at most 2 vectors that are linearly independent at every point. So how come we have 3 Killing vector fields that are independent in a two-dimensional space? Well, you see, at a point, we only have, at every point, we have a tangent space which is two-dimensional. Therefore, in that tangent space, you can have at most 2 vectors that are linearly independent. But these are vector fields. And the space of vector fields is infinite dimensional. And we have here 3 that are linearly independent of each other. So they are not pointwise linearly independent, but in the space of vector fields they are. So what is the role then of K3? The flow generated, the diffeomorphism flow, the isometric flow generated by K3 leaves a point, namely the origin, fixed and rotates everything about P. So we say that, here the definition is that the Killing vector fields which do not generate a homogeneity surface, in this case K3, the Killing vector fields which generate a trivial group orbit for at least a point are generating the so-called isotropy subgroup. Isotropy subgroup of the full symmetry group generated by all Killing vector fields. So we have that there are Killing vector fields which generate a homogeneity surface. These are the guys for which all points have non-trivial orbits. And then there are other Killing vector fields which do have points of trivial orbits, and we use it as a criterion to recognize them as rotations or generalized rotations because they have trivial orbits. Some points have trivial orbits, or some point has a trivial orbit, and those we will call the isotropy subgroup. Regarding the names, remember that you should be familiar with those names already. When we talk in cosmology about the assumption that the space-time is homogeneous and isotropic, what we mean by that is that the space-time is homogeneous in the sense that it has translation invariance. And when we say that the space-time is isotropic, we mean that it has rotation invariance, or generalized rotation invariance, including boosts, right? And so it's in the same sense that we use homogeneity here. This is the surface that you get when you, or the orbit that you get when you use Killing vector fields to generate those orbits, which do not have fixed points. So you're translating. And these guys have fixed points, so you're rotating. So this counts the number of translational degrees of freedom. This counts the number of generalized rotational degrees of freedom. So what is the dimension D of the isotropy subgroup then? In this case, it's generated only by K3, so it's 1. So the dimension of the isotropy subgroup D is 1, and the dimension of the homogeneity surface is 2, and the full number of Killing vector fields is 3, so we have 1 equals 3 minus 2. Very similarly, we proceed for cosmological models. The classification is with respect to the number of rotational symmetries and the number of translational symmetries. Technically speaking, the classification is with respect to the dimension of the isotropy subgroup D. So it's the number of Killing vector fields that have trivial orbits. Among other orbits, they have trivial orbits, so it's the number of rotations that we're counting here. And that can go up to 6 rotations and Lorentz transformations in the case of space-time, for 3 + 1 dimensional space-times. And second point of classification is the dimension of the homogeneity surfaces, and they can go up to 4. You can have up to 4 translational symmetries in time or any one of the 3 space dimensions. So for example, if the dimension of the isotropy subgroup is 0, we have no rotational symmetry. It's completely non-isotropic. If we have one rotational symmetry, then well, that could be a universe which has some sort of spin to it, but it still has one rotational symmetry axis. If we have that the number is 3, the dimension of the isotropy subgroup, then that is the case of FRW spacetimes, or FL spacetimes, where we have 3 rotational symmetries, but we don't have a Lorentz boost symmetry. The dimension of homogeneity surfaces, well, if it's 0, we don't have any translation invariance. Again, the case of S equal to 3 is the case most considered, which is where we have spatial translation invariance. But we might also have a time translation invariance as well. For example, de Sitter space, just like Minkowski space, would have all 4. It turns out that a large body of literature exists on most cases of pairs of D and S. It's quite surprising perhaps, but there are quite a lot of things known, often also exact solutions, for all kinds of combinations of non-trivial numbers of rotational and translational degrees of symmetry. So many exact solutions are known, many asymptotic behaviors are known. Even if the exact solutions are not known, the asymptotic behaviors are known. And a comprehensive text is the one by Wainwright and Edis. Here's the reference. Here's an example. You may see these keywords come up in talks and papers all the time. Here is the number of dimensions of homogeneity. Here's the number of dimensions of isotropy. So the number of translational symmetries, the number of rotational symmetries, and you get a special cases, so-called Einstein static models, Gödel's model, Kerr models, Friedmann-Lemaitre models are the ones with 3 translation and 3 rotation symmetries that we've considered so far. But then there are also cases where we have less symmetry. For example, we have the Bianchi models where we have translation invariance but not rotation invariance. Or we have full translation invariance but just one rotation invariance. And these are all very valuable to have because, and solutions to these models are very valuable to have because they give us insight into what the nonlinear structure of general relativity is capable of. But that's not the only way to classify models of cosmology. There's an alternative classification approach, which is based on classifying the energy-momentum tensor. And once we've classified the energy-momentum tensor, then that we can relate to the curvature tensors on the left-hand side using the Einstein equation. So the idea is a relatively simple one. The energy-momentum tensor is a symmetric operator. Ideally, we would sort of diagonalize it and get a classification, just like we classify self-adjoint operators, and then that gives us a classification of curvatures and therefore of spacetimes as well. It's not so easy though. Here's a proposition. For every physical energy-momentum tensor T mu nu, there exists a unique time-like vector field U, so that the energy-momentum tensor takes this standard form. Now that is way more general than the perfect fluid case that we had considered earlier. Because here we have more types of terms. We have mu times UA UB, and then where mu is just some scalar field here, and then we have terms like that where we have a vector field Q, and then the U again. You see, this is also a symmetric combination. That is symmetric in A and B. This is symmetric in A and B. But also that is symmetric in A and B. And then finally, there might be something that is tensorial and cannot be decomposed into an expression like this with a scalar function or like that with a vector function there. It might be truly tensorial. This decomposition, by the way, is similar to what you are probably familiar with from electromagnetism. You can always decompose a vector field in electromagnetism into a curl and a gradient. And the gradient part is the gradient of a scalar function. So a vector field can always be decomposed into something that's derivable literally by differentiation from a scalar function, plus the curl, which is truly vectorial. And so similarly here, we decompose this symmetric covariant 2 tensor into something that's ultimately tracing back to a scalar, something that traces back to a vector, and something that, and here again, scalar stuff, and here's something that is truly tensorial and cannot be decomposed. And that decomposition is unique if you require that these equations hold. So, for example, that pi is traceless and symmetric, and that makes it a tensor that cannot be expressed in terms of scalars and vectors. So any energy-momentum tensor can be decomposed in this way. And then this vector field U here, this time-like vector field U, is called the fundamental four-velocity field of the energy-momentum tensor. For a perfect fluid, it is actually the fluid velocity, but generally it doesn't have anything to do with any velocity of something's actually moving. The energy-momentum tensor may be due to some quantum fields, and there is no fluid actually moving. Now, in the case of a perfect fluid, the energy-momentum tensor has this much simpler representation. Okay, but what we had up there is more general. Now, the equation of state is the relationship between the pressure and the energy density, and we wrote the proportionality constant as W, but often W is also written as gamma minus 1, in which case, I'm just showing you that so that you're not too confused when you come across it in the literature. And then this gamma would be such that it's 1 for dust, W would be 0 for dust, it's 4/3 for radiation, W is 1/3 for radiation, and then it's 0 for the cosmological constant, W is -1 for the cosmological constant. And then the evolution of the universe, according to the current standard model of cosmology, would have a W parameter that is evolving roughly like this. And you may want to model that in your project, something like that, a curve like this, where W parameter starts out something perhaps around here, then drops very negative during the initial phase of cosmological inflation, then goes up all the way to 1/3 during radiation domination, and then drops down again, matter domination here where it's 0, and then it goes down like this to the current period of dark energy domination again. And it might even go smaller than -1. Okay. By the way, the situation can arise that a space-time has space-like homogeneity, so it has 3 translational symmetries, but it could be that the fundamental velocity field u is not actually orthogonal to those homogeneity surfaces. In that case, we say that this cosmology is tilted. It's just a piece of terminology that I wanted to know about. Okay. So then to the classification. A systematic classification of those T mu nus that we just found an expansion for can be performed by an analysis of its eigenvalues and eigenvectors. However, it's not simply the diagonalization of a symmetric operator, of a self-adjoint operator. It's not that. And the reason is this. Sure, the energy momentum tensor is a symmetric tensor, right? If you interchange mu and nu, you're not changing it. But the inner product in the space on which this thing lives is G mu nu, which is indefinite. And the spectral theorem doesn't apply when the space in which you're working is indefinite. You need a Hilbert space for the spectral theorem to hold. And that requires that the inner product is strictly positive, which it is not here. So T mu nu is actually, even though it's a symmetric matrix, it's not Hermitian. We can't use, or self-adjoint, we can't use the spectral theorem for it. Now let's try to evade that. We can lift one of the indices of the energy momentum tensor. If we do that, then the inner product in the space that we now obtain is no longer G mu nu. Now it's the Kronecker delta mu nu. Because if you use the metric with one upper and one lower index, then it's just the Kronecker delta mu nu. But the trouble is, well, then you have the benefit that you work on a space which has a positive definite inner product. But the price you have to pay is that this T mu nu is no longer symmetric. With one upper, one lower index, if you flip mu and nu, you don't get the same thing anymore. So either way, there's a conservation of difficulty in this. What you can then do is you can expand in a Jordan normal form, and that gives you, let me not go into the linear algebra of that, that gives you the Segre classification, which gives us 4 main types of energy momentum tensors, T mu nu. Okay. Remember the overall strategy. What are we after? We want a classification of energy momentum tensors because then, through the Einstein equations, that gives us a classification of curvatures, because that's on the right-hand side, curvatures on the left-hand side. And indeed, this is how it works. The Einstein equation, in 3 + 1 dimensions, And what I'm telling you now is a very curious fact whose significance I don't know, but it looks as if it could be very significant. In 3+1 dimensions, and only 3+1 dimensions, the Einstein equation can also be written in this form. Try it out yourself, prove this. The Einstein equation is normally of the form r mu nu minus 1/2 g mu nu r equal to some constant times t mu nu. This is the Einstein equation equivalently written in such a way that you simply have r mu nu on the left-hand side, and on the right-hand side you now have an expression that looks just like a mirror version of what the Einstein equation was. Now you have t mu nu minus 1/2 g mu nu t, where t is the trace of the energy momentum tensor. A very curious fact that's only true in 3+1 dimensions. So you see, if you swapped if you swapped r and t, and let this constant go into its inverse, then you get the Einstein equation again. Very weird. The Einstein equation in 3+1 dimensions has this duality between r and t. Strange but true. For our purposes, the only thing that matters here is that once we have a classification of the t mu nu's, we can plug them in here and we get the r mu nu. So what the Einstein equation tells us in this context is that the energy momentum tensor determines the Ricci tensor completely and only. The energy momentum tensor determines the Ricci tensor, but it does not determine the full Riemann curvature tensor. Very important. Okay, so if you know the energy momentum tensor, you can plug it in here, you get right away the Ricci tensor, 2 indices, but you don't get the curvature tensor with its 4 indices from that. This is something that's analogous to what's going on in electromagnetism as well. In electromagnetism, when you have charges, the charges and currents will determine electromagnetic fields, but not completely. There can be electromagnetic fields independent of charges and currents. If you have a box, and there are charges and currents in there, they will generate electromagnetic fields, fine. But there can be other electromagnetic fields on top of that. Simply, for example, light that you shine in from the outside that goes through the box. That light is independent of the charges and currents in there. And similarly in general relativity, matter plays the role of charges and currents. Matter will generate curvature, but there can be curvature that's not generated by the matter in there. In a particular volume, you could have, for example, gravitational waves passing through. They will not care about that. Okay, so it turns out that the Ricci tensor has 10 degrees of freedom, and they are completely determined by the energy momentum tensor. So the Segre classification of the possible energy momentum tensors, basically putting it into the Jordan normal form using linear algebra, gives via the Einstein equation a classification of possible Ricci tensors. But does this really give us a classification of the possible Riemann tensors with all of the 4 indices? No, not really. Because the Ricci tensor contains only 10 independent degrees of freedom of the 20 that are in the curvature tensor in 3+1 dimensions. Here's an important proposition. The information contained in the Riemann curvature tensor is shared among the Ricci tensor and another tensor called the Weil curvature tensor. The energy momentum tensor only gives us this. That's extra information. It's, for example, gravitational waves, as we will see in a moment. But it's also other things. So that means that using the Segre strategy of using the Jordan normal form for the energy momentum tensor gets us only that far. We still have to classify this Weil tensor. What is it? And how do we do the classification of it, and what do we get? Okay, here's the Weil tensor. The Weil tensor is this wild tensor here, lots of coefficients. And you recognize it's really the Riemann curvature tensor minus what you can generate from the Ricci tensor that has the right index symmetries of the Ricci curvature, of the Riemann curvature tensor. So basically, the Weil curvature tensor is the Riemann curvature tensor minus the Ricci curvature. This is the Ricci curvature. That's the part of the Riemann curvature tensor that is determined by the Ricci tensor. So indeed, if the Ricci tensor is given, for example, through the energy momentum tensor, and if also the Weil curvature tensor is given, then they determine together the full Riemann curvature tensor. Namely, in this way, the Riemann curvature tensor is the Weil tensor plus all of this business here. Okay, so here's the crucial equation in the yellow box. The Riemann curvature tensor can be expressed through the Weil curvature tensor with its 10 degrees of freedom and the Ricci tensor with its 10 degrees of freedom. In other words, the Weil curvature tensor contains all that curvature information which is not determined from the energy and momentum. The Weil curvature, therefore, describes all that curvature which can exist even where there is no matter. Where there is matter, space will be curved. But outside of regions where there is matter, space can still be curved. Obviously, it would be weird if it were completely flat the moment you go to places where there is no energy and momentum. But you see, the energy momentum tensor gives you locally a contribution to the Ricci tensor. And it's totally local. Where the energy momentum tensor vanishes, the Ricci tensor vanishes. So the Weil tensor describes all that curvature which can exist even where there is no matter. Just like electromagnetic radiation that can exist even where there are no charges and no currents. For example, gravitational waves here. Now the Weil curvature tensor has a particular property under conformal transformations. So that brings us back to the study of conformal transformations earlier today. Assume mg is a 3 + 1 dimensional space-time. Choose an arbitrary smooth positive scalar function phi for the purpose of local rescaling of local conformal transformation. Namely, we use this function phi to define a new space-time, which is the same as a differentiable manifold, but we equip it with a new metric. And the new metric is the old metric, except that we multiply with this conformal factor. So the G tilde metric is the G metric multiplied with this conformal prefactor here. A positive, smooth positive scalar function. Then this will change, I mean the metric changes, so the curvature tensor will change. But it turns out that the Weil curvature tensor does not change. The Weil curvature C tilde comes out to be the same as the Weil curvature C. In other words, the Weil curvature tensor is invariant under local covariant transformations. If you know the causal structure of a space-time, you can determine the Weil curvature tensor, because it doesn't depend on the scalar prefactors. You can intuitively think of it this way, that the Weil curvature will distort shapes. So let's say you have a circle in your space-time. As Weil curvature is present, it might turn it into an ellipse, maybe this way or that way. But what Weil curvature cannot do is change the overall size of it. Wild curvature, it's the Ricci curvature that actually changes the size of circles or objects. So for example, when a gravitational wave passes through a gravitational wave detector, it will turn circles temporarily into ellipses in this way, while not making them bigger or smaller. It will just do this with them, because it's wild curvature that passes through. A little historical remark. Consider the equivalence class of spacetimes that are conformally equivalent to Minkowski space, in the sense that consider the set of spacetimes that are that have the Minkowski metric up to a scalar prefactor. So up to local conformal transformations, it's just like Minkowski space. This was Einstein's first guess, because it's much simpler than actual GR. Einstein and a collaborator by the name of Fokker initially considered such a theory, in which the metric is the Minkowski metric up to just this prefactor here. And the idea was that this prefactor would play the role of the Newtonian potential. And they could get Newtonian gravity as a limiting case from that. So this would be a gravity that has only a conformal degree of freedom, which in particular, therefore, would not have wild curvature. Wild curvature is completely insensitive to such a thing. In this case, they would write the action in this way. I think they didn't actually write the action, they only wrote with the equations of motion, but you could write the action in this way. And you vary now with respect to the only degree of freedom in your theory, which is the phi, and not really the full G mu nu, but only the phi, because, you know, the G mu nu is this times eta mu nu, so you don't vary with respect to eta because that's fixed, you only vary with respect to phi. And then your equation of motion, your simplified Einstein equation, is that the Ricci scalar is equal to the trace of the energy momentum tensor. In this case, for example, electromagnetism would not gravitate. And that's because the electromagnetic field has a traceless energy momentum tensor. So the electromagnetic field wouldn't be gravitating. It turns out that the equivalence principle is still okay. You can still make it a completely covariant theory. But when he calculated the perihelion shift of Mercury, he didn't get the right answer, because it's really a different theory. And also the light bending would come out incorrectly. So he gave up on that, and then the next step was full GR. Okay, so via the Einstein equation, the Segre classification implies a classification of the Ricci tensors. But then we said that the Ricci tensor is not giving us the full curvature. There is also the wild curvature tensor that we cannot get at. So the energy momentum tensor and its Jordan normal form. So we need to do a classification of possible wild tensors as well. And that is the Petrov classification. As we said, it has 10 degrees of freedom. The Riemann curvature tensor has 20. And the wild curvature tensor has the same index structure as the Riemann curvature tensor. It has the antisymmetry in here and the symmetry in there. And it is antisymmetric, it's antisymmetric in rho epsilon, antisymmetric in mu nu, and it is symmetric under this exchange. If you exchange these two, just like the Riemann curvature tensor, you have a symmetry. So you might think this is great. Maybe we can diagonalize that. So we can view that tensor as a map from the space of antisymmetric contravariant two tensors into the space of antisymmetric covariant two tensors. You see, if you take an antisymmetric contravariant two tensors, so a tensor with two upper indices, antisymmetric, contracted with a Weyl curvature tensor, then those indices contract, and you're left with those two upper indices, which are contravariant antisymmetric. So the Weyl curvature tensor can be viewed as a linear map of contravariant antisymmetric two tensors into contravariant antisymmetric two tensors, so-called bivectors. But the trouble is that the inner product in that space of antisymmetric two tensors is not positive definite. We have two indices here, right? Two indices down here, two indices up there, and the inner product in that space is not positive definite. So therefore C is, in the Lorentzian case, again, generally not Hermitian. And therefore we need to use the Jordan normal form again. By the way, the same argument can be made, of course, for the Riemann curvature tensor. Now, in the case of Riemannian manifolds, this inner product space is positive definite, and you can diagonalize the Riemann curvature tensor then, and its eigenvalues are essentially the so-called sectional curvatures, which are yet another way of describing the curvature of a manifold. They're basically the tidal forces. Okay, so but here we don't have, on space-time, this is not a self-adjoint operator. We have to do the Jordan normal form for the Weyl curvature tensor. And if we do that classification, we get 6 main Petrov classes for the Weyl curvature, according to the eigenvalue eigenvector decomposition. And roughly speaking, here is the outcome. I mean, I just give you a few comments on what the variety is, what's on offer, what is possible in general relativity. So there is type 0 or type O Weyl curvature. That's simply the case where there is no Weyl curvature, it's only Ricci curvature. So there's only curvature in this case where there is matter and where there is radiation. Then there's type D Weyl curvature, and that is very important. It's all over the place. That is static Weyl curvature. This is the kind of Weyl curvature that you get from a star, outside of the star. For example, we are exposed to the Weyl curvature of the sun. The sun is curving space where it is, but also in the vacuum around, space is still curved. This cannot be Ricci curvature. Ricci curvature is determined by the energy momentum tensor, and if that's vanishing, the Ricci curvature is vanishing. No, it's Weyl curvature. It's the type D Weyl curvature that we see here. And then there's also transverse gravitational waves. That's type N. Transverse gravitational waves, the type that LIGO and LISA are aiming to detect. Just like light, the transverse gravitational waves have their strength decay like 1/r. It's just like in electromagnetism, gravitational waves just like electromagnetic waves. Just by dilution of the photons or dilution of the gravitons. Or the amplitude, if you want to think about it gravitational, classically. Now in principle there are also type 1 so-called longitudinal gravitational waves. These are technically shear waves. They cause a shear effect on the matter that they act on, and we will later see this sort of thing occur in much more detail. However, they are a near field effect. They are not traveling waves. They are not traveling very far. It's the same in electromagnetism. When you are close to an antenna, then the field that you see is of a different, qualitatively different kind than if you're far from an antenna. If you're far from an antenna, you just get the traveling waves that induce each other. You know, a decaying magnetic field produces an electric field, then the electric field decays, produces a magnetic field. This sort of thing is self-sustaining. That's what you see at long distances. If you're close to the antenna, you see near field effects that decay very quickly. Similarly, in gravity, you get these near-field effects that decay much faster, and they don't travel on, they don't carry energy away. So you have those type 1 longitudinal gravitational waves as well for gravity. You wouldn't expect to see any of these in LIGO, because they don't travel that far. Well, and then there are other types which are basically mixtures of these wild curvatures. Finally, let me mention that, and that will guide some of what we do next in the course, there are potential problems with all those symmetries and idealized cases. You see, when we look at highly symmetric solutions, for example, of the Friedmann-Lemaitre type, then they may possess properties that are peculiar to high symmetry. For example, when a Friedmann-Lemaitre solution or a Schwarzschild solution exhibits a singularity, we have to ask, is that singularity generic? Is that a robust conclusion that we can draw? What if we look at a situation that's not as ideal, not as symmetric? Do we still have a singularity? This is a very serious concern, considering that in Newton gravity, it would make all the difference. If, for example, you take a star, according to Newtonian gravity, and you have it collapse onto itself in a completely symmetric fashion, then in principle, well, the potential is bottomless, and it would just collapse into a point eventually. In Newtonian gravity, there's nothing to prevent that from happening. You could have a singularity forming. No, not really a black hole in the sense of a horizon and all that sophisticated stuff is not coming up, but it could collapse into a singularity. But in Newtonian gravity, if the star starts out with just a little bit of a rotation, you just tip it a little bit, it's no longer happening. It's no longer happening because as the thing is compressing and compressing, it starts spinning faster and faster. It's just like the figure skater effect, and eventually the whole thing will fly apart again. So there's a huge difference between the idealized, completely symmetric solution, where you actually have everything crunching into a point, and a little bit perturbed, where it's no longer true. So we have to worry in the case of the Schwarzschild solution or of FRW solutions. We assume so much symmetry. What if we give up on that symmetry? Maybe the whole thing goes out of the window. It's no longer true that we have the Big Bang singularity or that we have the black hole singularity. That's why in the 60s and early 70s, Penrose, Hawking, and others worked on singularity theorems to show that GR is really different from Newtonian gravity in the sense that it actually guarantees singularities. GR is predicting its own downfall through its dynamics. Right, we will study how GR is predicting its own downfall in lectures that are coming up. Okay, that's it for today.